Okay, welcome everyone. Um, as I posted in the Slack, it turns out the breakout room problem last time was a Zoom-wide system issue, so hopefully that won't happen again. So today I'm going to continue with a brief discussion of spherical geometry and then go on to our main topic for the next couple of lectures, which will be hyperbolic geometry, both of surfaces and of higher dimensional manifolds. But before I start, I wanted to, let me first ask a question. How many people know the problem about getting a fox, a goose, and a bag of grain across a river? Press yes in your, okay. And press no if you've never heard of this. A couple people haven't weighed in yet. Let me remind people, it's very helpful if you could share your video if you're willing. Okay, so actually we have 7 yeses and 8 nos. Does somebody who said yes want to explain what the problem is? How about Ethan?
Oh, okay. So I'll be honest, my yes is a half yes because I have definitely seen it before, but I do not remember all the details.
Yeah, let me try, so since we have lots of yeses, let me try Matthew.
So if my memory serves, the problem is you have a river and a fox. I don't remember what specific items you said. Fox.
Goose and a bag of grain.
Fox, goose, and grain on one side of the river that you all want to bring to the other side. And if you leave the fox and the goose alone, the fox will eat the goose, so that's a problem. If you leave the goose and the grain alone, the goose will eat the grain. And you have a boat that can bring you and one other item to the other side.
Exactly. Okay, so I won't go to the solution of the problem, but if you do, it has some odd resonance with the dyslexic issue I was confronting in the Hopf proof, which I'll mention at the end. So let me do the Hopf proof again of mixing, just do it right. Sorry for the confusion. And I'm also, let me just explain a method for doing it right, which I should have employed last time. So remember, the main thing we want to use is the fact that if we average along an orbit of the irrational flow and then apply our transformation t, this turns out to be the same as averaging along a very long, a longer orbit with t on the other side. And here lambda is greater than 1. It's the leading eigenvalue of our toral automorphism. And if you iterate this, then you get lambda to the n. And if we take 2 functions that are of mean 0, then we have the nice property that if you start averaging any one of them, say if you start averaging g, that this will tend to 0 in L2. And we wanted to exploit that fact to get mixing. And the other fact is that if t is small, then if you average a function, then you get that st of f is very close to f in L2. That's actually true if it's L2 or if it's obvious if it's continuous. Okay, so the way to try to do the proof without getting confused is to start in the middle. So we know we want to use this identity at some point. So one way to do the proof is to write that the inner product of f with, let's say, t to the n st of g is equal to the inner product of f with s lambda to the n t t to the n of G. So that's the identity that we wanted to use in the proof. And now we just have to work backwards and forwards until we get a proof of mixing. And so this is a little bit of the duck and goose thing, as you'll see when the proof is complete. The problem, I'd like to assert that this term tends to 0. But so I'd like to say, oh, well, I'm averaging over a very long flow line, so that tends to 0, right, by this property. But no, I don't have a fixed function here. I have t to the n of g. So two things are changing at the same time, and I can't assure that this tends to 0. So the key point is that this operator is self-adjoint, since it involves both h and h inverse, the flow and going forward and backwards. And so I can move this to the other side and write this as s lambda to the n tf applied to Tn of g. And now f is not changing. So this tends to 0 in L2. And the norm of this is always the same because t is unitary. The norm of Tn g is the norm of g. So by the Cauchy-Schwarz inequality, the whole thing tends to 0. So that's good, but what does that have to do with mixing? Well, now we have to work in the other direction. So what we do is we use the fact that t is unitary. It's almost self-adjoint. So we can write this as t minus n f st of g. And actually, maybe I should have put g here. So if you smooth g just a little bit by averaging along an orbit, you barely change it. So this is approximately the same as t to the minus nf g, which is the same as f t to the mg. And so altogether, we've proved that the inner product between f and t applied to a high iterative t applied to g tends to 0 whenever they both have mean 0. And that's the mixing property. Okay, I say it again because this is really a central theme in dynamics, and we're going to use it when we get to the horocycle flow on a hyperbolic surface. Okay, so now let's go back to geometry, especially spherical geometry. So here's a little point. What is geometry? So in many instances, the modern perspective about geometric structures is the notion of a GX space. And this means a space that's locally modeled on X up to the transformations provided by G. So in our case, X will be always some sort of, well, this will be some sort of space, and this will be some sort of Lie group. And usually, this will come with a Riemannian metric. Certainly for hyperbolic and spherical geometry, it comes with a Riemannian metric. But just if one wants to formalize what it means to talk about spherical, Euclidean, or hyperbolic geometry, it's really a discussion of not a space with a metric, but really this pair. And the Lie group plays a more and more central role as one goes deeper into the theory. And this Lie group acts on this space. And often we want it to act transitively. That's the notion of a homogeneous space. And there's even more could be true. It could act transitively on unit tangent vectors, in which case the space is a symmetric space. And then it has constant curvature, and that's what we're discussing. Okay, so spherical geometry, we can take our group to be SO3, sitting inside of the linear maps on R3, and to take our space X to be the standard two-sphere. So it's the set of points. And I'm going to start writing the inner product of a point with itself as p squared. It's thinking of this as a quadratic form or a dot product. So S is the two-sphere, the beautiful two-sphere is just a set of vectors of norm 1 in R3. And it's often nice to think of it as having a north and south pole and an equator. I'll choose my coordinates. So this is X and Y. This direction is Z. And we have a metric on this space. So the metric is, of course, the induced metric. We just take the metric on R3, the Euclidean metric there, and restrict it to the sphere. And since SO3 preserves the Euclidean metric, this metric on X is also preserved. And G acts transitively. Just because the orthogonal group acts transitively on vectors, you can take a vector and move it to any other vector of the same length. So it acts transitively. On the sphere, even better, the stabilizer of the North Pole consists of rotations around the equator. That moves any vector at the North Pole to any other vector of the same length. And so it has this isotropy property, which gives it constant curvature. The curvature turns out to be 1, as you would guess. Constant curvature 1. And for future reference, I want to talk a little bit about the interaction between the geometry and the inner product on the space R3. So there's some linear algebra sitting here because R3 comes equipped with this inner product. And so, for example, if we take 2 points on the sphere, we can think of them as being represented by unit vectors in R3. And then we can form the dot product between these 2 vectors. Alternatively, we can measure their distance along the sphere. Their distance will be exactly equal to the angle the 2 vectors make, because on the sphere, the geodesics are great circles, and the length of an arc of a circle of radius 1 is the same as its angular length. So the metric has the property that the inner product, P dot Q, for any points on the sphere, is equal to the cosine of the angle, which is just the distance from P to Q. Okay, so the inner product is telling us the distance between points. That's a nice way to get to the inner product without having to write down the distance, without having to write down any Riemannian metrics. Now, I mentioned that the geodesics in this space, the complete geodesics, are great circles. That is, they are circles centered at the origin. So the prime example is the equator. And the equator is naturally parameterized by traditional trigonometric functions. So you could parameterize the equator as the locus cosine s sine s 0. That gives a unit speed parameterization of this geodesic. And of course, other geodesics are the lines of latitude. And then there's some other circles that are kind of interesting. For example, the lines, this line of longitude, all the lines of longitude are geodesics. Then there's these circles here. Those circles, or this circle here, there's lots of circles on the sphere that are not great circles. They're not centered at the origin. What is the geometric meaning of a circle like this? How could you describe that circle using the geometry?
Curvature?
Louder?
Constant geodesic curvature?
Yeah,
So
that's true. This is a circle of constant geodesic curvature. And one way we know that is that it's invariant under the rotations of the sphere. So it has, whatever the curvature is at one point, it has to be the same. How about another description using the distance on the sphere?
Are the latitude lines like all the points a set distance from one of the poles?
Yes, very good. So another description of a latitude line is the following. If you're at 20 degrees latitude, it just means that when you draw a geodesic from the North Pole down to that circle, the length of that geodesic is 70 degrees turned into radians. And so this is nothing more than the boundary of a ball around at the North Pole of radius 70 degrees. So this is really just a metric circle. I like to think of it as the boundary of a ball around the North Pole of radius 70 degrees. And similarly, we can also think of it in the following way. It's a parallel of the equator. Now in spherical geometry, there are no parallel lines. The traditional definition of parallel geodesic lines is that they don't meet. And any two circles that are not the same do meet, any two great circles. So what a parallel means is a curve that's at equidistance from a geodesic. We'll meet those also in hyperbolic geometry. And so this is, if you like, it's part of the boundary of a tube of width 20 degrees around the equatorial geodesic. Okay, so one reason I bring up these circles is that you might ask, how do I know the equator is a geodesic? So let me give you two proofs that the equator is a geodesic without using the Euler-Lagrange equation or something terrible like that. In the case of these very symmetric spaces, it's like we're doing Euclidean geometry. You don't need to use differential geometry very much in the plane and also in these spaces of constant curvature. So we could ask, if we have two nearby points on the equator, is there another path between them? Is this really the geodesic, or maybe the shortest path between them goes something like this? After all, the latitudes are shorter than the equator. Maybe you can take a shortcut by going into the southern hemisphere, going quickly along a latitude and then coming back. So proof one that these are geodesics uses reflections. So if you believe that the geodesic joining two nearby points is unique, which is a basic theorem in Riemannian geometry, then it has to be invariant under any isometry that fixes P and Q. Well, there is an obvious isometry of the sphere that fixes P and Q. It doesn't preserve orientation. It just reverses the northern and southern hemispheres. It's reflection through the equatorial circle. And whatever this geodesic is, it has to be invariant under that isometry because that fixes P and Q. But if it's straight into the southern hemisphere, then you would get a different geodesic. So in fact, the geodesic has to lie on the fixed point set of this involution, and therefore it has to lie on the equator. Okay, so that's one proof, and it works for many rather symmetric spaces, but it used uniqueness of geodesics. What if we just say a geodesic is the path of shortest length between 2 points? Can we find a proof just straight from the definition? Well, we can, and this proof is given a little more clearly, I think, on a longitude rather than the equator. So suppose we pick 2 points on a longitude, and we think that this arc along the longitude is the geodesic joining them, but what about a competing arc like this? Could this possibly be shorter? Well, the beautiful fact is that there's a projection from points near this arc on the longitude to the longitude. There's a retraction where you move along the lines of latitude. And when you take this wobbly geodesic and project it onto the line of longitude, it gets shorter, right? Because you haven't changed the length of the component of the vector pointing north, but you've killed the component of the point of the vector pointing east and west. And so this projection shortens the lengths of paths unless the path happens to be entirely vertical, in which case it has to be the longitude itself. Okay, so that is actually a simple explicit shortening procedure allowing you to see that these are geodesics. Now, as we know from Euclidean geometry, geodesics, or edges, shall we say, or lines, play just as important a role, if not a more important role than points. So we might ask ourselves, how do we describe all of the geodesics on the two-sphere? And a nice way to describe a geodesic is to simply take the plane it spans and then take a normal to that plane. And then we can call this geodesic CP. It's uniquely determined by a point on the sphere. And in fact, there are 2 points that determine the same geodesic. And if we choose an orientation for R3, then the choice of P or minus P gives us an orientation of CP. So once we know what P is, there's a unique orientation of CP such that it satisfies, say, the right-hand rule. And consequently, we find that the space of oriented geodesics is naturally identified with the sphere itself. So the set of oriented geodesics on the two-sphere is naturally isomorphic to the two-sphere by P goes to CP. And so again, we can talk about inner products, and there's a natural invariant when you have 2 great circles. Namely, any 2 great circles do meet in a point. So this one is, say, this is supposed to be the center of the sphere. This one is CQ, let's say. And there's a dihedral angle here, alpha. Now, whenever somebody starts talking about angles between geodesics, you should get worried because there's this angle, but then there's also this angle. So is the angle actually well defined? But it is, because these are oriented geodesics. So you can ask, how far do I have to turn CP so that it coincides with CQ? And that's what this angle alpha measures. If I tried to turn it through this angle, I would again get it to CP, but the orientations would not agree. Now you might say, well, I could turn it P to Q or Q to P. So if you interpret this as either being an angle with an ambiguous sign, or you always require it to be positive, either way, you have a well-defined dihedral angle, and especially the cosine of that angle is well-defined. So that's called the dihedral angle between the dihedral, let me just call it the angle. That's called the angle between a pair of oriented geodesics. And I say dihedral because they span planes in R3, and it's also the dihedral angle between those planes. So this angle, alpha of CQ, is of course also has the property that its cosine is equal to the inner product between P and Q. So the inner product provides us a way to measure both distances and angles on the sphere. Okay, so let's do, let me do a quick question. How do I find out where CP crosses CQ? Where is if I give you two great circles, how do I find one of these points where they cross? I mean, I give you literal points on the sphere. How do you find this point of intersection?
Cross product?
Yes, the good old cross product from multivariable calculus. This is P cross Q, and of course there's 2 points, so it's also Q cross P. So the cross product is something you should keep in mind if you're doing actual calculations and I give you 3 circles and you want to find the vertices of the corresponding triangle, this is a simple way to do it computationally. And that's just because the circle, what is the circle after all? It's just the locus of points that are perpendicular to P. So CP, if you like, is the same thing as P perp. And these are all, facile remarks. One reason I bring them up is that when we go to Minkowski space, there'll be analogs that are less familiar, but equally simple. Okay. So now let me talk a little bit about, one other remark. So you might think of the 2-sphere as a model for geometry, where lines are great circles, but it has this unfortunate fact that lines meet in 2 points rather than 1. And of course, this is rectified by taking the projective space, RP2, which is S2 modulo the antipodal map. This is a non-orientable space. And then you let the circles go down to lines here. And this gives a model for geometry that's like Euclidean geometry, but has the interesting property that every pair of lines meets. There are no parallel lines. And that's a virtue for 2 reasons. One, you can treat lines uniformly. There are no exceptional cases coming from parallel lines. And 2, it proves that Euclid's 5th postulate was independent. Namely, this geometry satisfies the first 4 axioms of Euclidean geometry, but it doesn't satisfy the parallel hypothesis because there are no parallel lines. And that's a general principle in logic to show that a set of a 5th axiom doesn't follow from 4 given ones seems very hard. How would you ever figure out everything you can deduce from 4 given axioms? Well, the answer is if the 5th axiom is independent, you should be able to find a model that is a space with an interpretation of the words like points and lines where the first 4 axioms are true and the 5th one isn't. And that's what spherical geometry does. It's often thought that hyperbolic geometry was, when invented by Lobachevsky, was the sort of first way to show that the parallel postulate was independent, but of course there's this much simpler way as well. Okay, so now let's discuss, if we have points and lines, let's discuss the simplest geometric figure, which is a triangle. Well, actually, last time I discussed looms, which are also important. But let's go to triangles. So I mentioned last time a basic theorem, which says that the area of a triangle is given by its angle defect. So alpha plus beta plus gamma minus pi. And this is easily proved using the idea that this triangle can be written as an intersection of looms. So I'll leave that to you, but I want to exhibit another theorem, which is elementary, but which has a slick proof, which will be useful again in more general settings. It's a very powerful, simple technique to know to transparently see certain assertions. So this theorem says every triangle that can exist does exist. So given, let's say alpha, beta, gamma in 0 pi, there exists a spherical triangle with these angles. And these are interior angles. If and only if the positive area is positive, so alpha plus beta plus gamma is greater than pi. Okay, now one way you might try to prove this is just start with 2 circles that meet in angle alpha, and then start moving the 3rd circle and try to achieve beta and gamma by some method of continuity. And that would probably work, but it wouldn't be a very fast way to actually determine, say practically, what the vertices are of a triangle like this, how to explicitly exhibit it. And so I want to mention another method which goes back to freshman linear algebra, the classification of quadratic forms. So the idea of the proof is the following. The key feature of a triangle is not so much these angles as these edges. And let's orient the edges in a clockwise or counterclockwise pattern. In any case, let's orient them consistently. So from alpha, beta, and gamma, we get 3 great circles, which I might call CA, CC, and CB. 3 oriented great circles. And knowing the angles are the dihedral angles between these circles. And so they tell me the inner product of C with B, or at least the cosine of that inner product. So just looking at this triangle, I get 3 vectors in R3, and I get to know all of their inner products. And that should be enough information to determine the 3 vectors. So the proof is all we want are vectors A, B, and C in the 2-sphere, or in fact in R3, such that the matrix of inner products, Vi.Vj, if you think of this as V1, V2, V3, this matrix has the following form. So these vectors should lie in the sphere, so their inner product with themselves is all 1. And then the inner product of A with B, for example, should be the cosine of this remaining angle. So it should be the cosine of gamma. So here we should see the cosine of gamma, but actually it comes with a minus sign. And then here we'll see minus the cosine of beta, and here minus the cosine of alpha, and then the matrix is symmetric. So the same numbers down here. Why is it minus cosine alpha? It's because for example, to rotate CA to CB, you don't move it through this angle, you move it through this angle because of the orientation. So the angle in question is actually the complement of gamma, pi minus gamma, and the cosine of pi minus gamma is minus cosine gamma. Okay, so we get this symmetric matrix. This symmetric matrix determines a quadratic form on R3. Now, what can we say about this matrix? Well, if the determinant is non-zero, then we can change coordinates so the matrix is one of the standards ones. It has signature 3, 0, or 2, 1, or 1, 2, or 0, 3. But it's pretty clear that since the cosine is less than 1, this top corner here gives a subspace of signature 2, 0. It's positive definite. And so the signature will either be 2, 1, or 1, 2, or 2, 1, or 3, 0. Well, the beautiful fact that you can check is that the determinant of Q is positive if and only if alpha plus beta plus gamma is greater than pi. So that's a calculation involving cosines. I won't go through the details. Maybe I'll let you do that. But the upshot is that this condition implies that this matrix is similar to the diagonal matrix because it has a positive definite part here, and the product of its eigenvalues is positive. So they would have to be, it has to be of type 3, 0. So this implies, if we have this condition, it implies there exists a change of coordinates such that R3 Q goes over to R3 and the usual inner product, which is given by the identity matrix. So in detail, that would mean that A transpose QA is equal to the identity. In other words, we can do the Gram-Schmidt process and find a vector, say the first one of norm 1, then make the second vector orthogonal to that, etc. And now, what happens under this change of coordinates? Well, here we have the 3 standard basis elements, E1, E2, and E3, and they go to 3 new vectors over here. And let me call those vectors A, B, and C. Well, since the quadratic form here goes over to the standard quadratic form there, the image of the standard basis here gives 3 vectors on the unit sphere in R3 because of the fact that their inner products are 1 with the desired angles. And so the image of the standard basis here under A solves the problem for us. In other words, this basic theorem on the classification of quadratic forms can be used and really underlies the construction of triangles with prescribed angles. This also highlights a beautiful fact about hyperbolic and Euclidean geometry. So what would happen if the determinant came out negative? This theorem, this proof would not work. There would not exist, if the sum of the angles is less than pi, there is no spherical triangle with these angles. But what does the theorem tell us? What does it tell us about this quadratic form? Well, it had a subspace which is definite of signature 2, 0. If the determinant is negative, the whole quadratic form has signature 2, 1 instead of 3, 0. So what happens is if the determinant of Q is less than 0, then you find that Q is equivalent to the standard quadratic form of signature 2, 1. In other words, 1, 1, minus 1 on the diagonal. And as we will see shortly, this will imply that there exists a hyperbolic triangle with these angles. So the same proof allows us to take prescribed angles and construct a triangle. And the beautiful idea here is that the triangle wants to live. The triangle exists somewhere. The only question is, where does it exist? And that depends on the signature of this quadratic form. So in the case of XX angle, it's able to live in spherical geometry. In the case of a negative, a loss of angle, a negative angle defect, it lives in hyperbolic geometry. And so that's a really strong and powerful idea, that you're trying to find a geometric object, and the geometric object will seek the space it wants to live in via some sort of signature condition, in this case on the quadratic form. Okay. So now, let me remind you, we were doing the uniformization theorem. And the uniformization theorem said that if you have a Riemann surface, that its universal cover was isomorphic to the Riemann sphere, the complex plane, or the hyperbolic plane. And we've been studying this case. But as you know, there is no subgroup of symmetries of the Riemann sphere, finite subgroup, that doesn't have a fixed point. Every transformation of the Riemann sphere has a fixed point, every automorphism. So you might say the only Riemann surface modeled on the sphere is the sphere, and that would be correct. However, it's useful throughout geometry to broaden our perspective and allow groups with torsion. So we could ask ourselves, what are not the manifolds with constant curvature 1, but also the orbifolds with constant curvature 1? So what does it mean for X to be an orbifold with constant curvature 1? a 2D-dimensional orbifold with constant curvature 1, well, this is tantamount to saying that we can write x as the quotient of the two-sphere by the action of a finite group of symmetries. So gamma is contained in the isometries of the two-sphere. If the orbifold's oriented, then I can take this group to be also orientable. So this is SO3. And this group should be discrete. But the isometry group is compact. It's covered by S3, and so it has to be finite. And the finite quotients of S2 yield objects that are not quite manifolds. They're objects that are locally modeled on quotients of, say, a disk on the two-sphere by the action of a finite group of rotation, which nevertheless are worthy of geometric study. These are called orbifolds. So for example, if you were to take the rotation around the equator by 180 degrees, this has two fixed points. And the quotient space is topologically a sphere, but geometrically, the two fixed points look singular. You get what's sometimes called the lemon. And we record the fact that these come from the action of a group that fixes this point and that the stabilizer has order 2 by writing the number 2 next to those points in the quotient orbifold. And if you were to measure the angle around these points, you would get 180 degrees rather than 360 degrees. But they are literally modeled on the quotient of a neighborhood of this point, a spherical disk, by rotation by 180 degrees. So this is what's called the 2-2 orbifold. And actually you could say, oh, what about other finite groups? So another nice group to add in is what happens if we throw in rotation by 180 degrees this way. What will that give us as a quotient space? So in fact, what is the group generated by 180 degree rotation around the equator and 180 degree rotation fixing the north and south pole? What's the order of the group generated by those two elements?
4.
4, who said that?
Hello.
Hi, okay, let me make sure I'm on speaker view. That's right, so the product of these two rotations, beautifully, is just rotation around the third axis in the picture. This is a copy of a Klein 4 group, Z mod 2 across Z mod 2. And it gives a quotient of the sphere, which looks more like this. It's actually obtained by taking two quadrants in the northern hemisphere and gluing them together back to back. And in fact, this quotient, we've just made the group bigger. So we have covering maps of orbifolds going from here to here and then going from here to here. And there's a deck, there's the deck group here, Z mod 2. We can think of this intermediate space as a Galois cover of this orbifold. Namely, this lemon has a symmetry where you rotate around an axis in the middle. And when you do that, these 2 points get identified, say at this point, but then you introduce 2 new orbifold points, say here and here. So this is a simple instance of the theory of orbifolds. And in this theory, all of these maps should be regarded as covering maps. They're not branch covers. The fact that this is an orbifold rectifies the branching behavior of the mapping. In particular, the area of this guy is just the area of the sphere divided by 4. As is clear, the metric down here just comes from the metric up here by taking the quotient. Okay, so let's ask an interesting question then. So here's a basic fact about covering spaces. If you have a covering of any reasonable spaces, say X maps my topological covering space to Y, so say both of these are finite complexes, then the Euler characteristic of X is equal to the degree of the covering times the Euler characteristic of Y. For example, when this is an ordinary covering map, you just triangulate Y, and then every 0 simplex down here has D copies up here. Every 1 simplex has D copies up here. And so if you write the Euler characteristic as an alternating sum of the number of simplices of a given dimension, everything clearly multiplies by D. Well, this principle also applies for orbifolds, provided we know how to calculate the Euler characteristic of an orbifold. And so let me tell you how you do that. So the Euler characteristic of let's say a closed surface orbifold, or closed two orbifold, I guess I should say, of genus G is what? So we have a surface of some genus, and then it's going to have some points on it which are orbifold points. They're actually cone points. And these cone points are going to have integers attached to them, say n1, n2, etc., up to nk. Okay, so what's the Euler characteristic? Well, first, the Euler characteristic of, let me give this object a name. Maybe it should be y since it's the quotient. The Euler characteristic of y without the orbifold points is just the Euler characteristic of a surface of genus G. So the Euler characteristic of the two-sphere, as we all know, is 2. For example, the homology is supported in dimensions 0 and 2. 1 plus 1 is 2. Every time you add a handle, you add z plus z to h1, and so you have to subtract off 2g. This is in the orientable case. And now, if we were to remove these points, these orbifold points, just take them out, every time you remove a point, you're removing a 0 simplex from the space, so you reduce its Euler characteristic by 1, so minus k, where k was the number of orbifold points. So that's what we would get if we literally took these points out. But they're actually there. But how should we count them? Well, this point here is double covered by a single point upstairs. So to get the count to work out, we think of this point as really half of a point. The presence of this non-trivial stabilizer, or the absence of a full cone angle here, we only see a fraction of the desired cone angle, means this should be thought of as less than a point. The size of the count should reflect the size of its tangent space. And so what we do is we count an orbifold point of order n as an ordinary point divided by n. So we have to add those back in. So the sum from 1 to k of 1 over n sub I. Okay. And with this convention, this theorem about the covering of, this theorem about the multiplicativity of the Euler characteristic works. So let's do this in particular in the case where y is equal to the two-sphere with, let's say, 3 orbifold points, n1, n2, n3. So what's its Euler characteristic? It's the Euler characteristic of the sphere minus the 3 points we've taken out plus 1 over n1 plus 1 over n2 plus 1 over n3. But if y is a degree d quotient of the sphere, then this should be the Euler characteristic of the sphere, which is 2, divided by some integer d. And in particular, it should be positive. So, but what we have is 1 over n1 plus 1 over n2 plus 1 over n3 is, that says this sum here must be greater than the negative of this. So this must be greater than 1. And there's only finitely many triples of points that, triples of numbers, integers, with this property. So some examples are a half plus a half. Oh, that doesn't quite make it. So the next number better be at least a third. So a half plus a third plus, and now if I were to put a sixth here, that would equal 1. Oh, so that's no good. So let's cross that out and do a half plus a third plus a fifth. So that's definitely going to be greater than 1. And then we could also do a half plus a third plus a quarter, a half plus a third plus a third, plus a third. And now we're kind of stuck. Those seem to be all the examples. Okay, so it looks like we should be able to construct orbifold points, orbifold quotients of the sphere with signatures 2, 3, 5, 4, and 3, but probably no others, just by this simple Euler characteristic calculation. And in fact, that's a theorem. And so let me just state this theorem, which is classical and which you probably have already seen the proof of. The theorem is, and I'll state it in a slightly weaker form than what one would like to use, is that the discrete subgroups of SO3 are isomorphic to Z mod n, any n greater than or equal to 1, to the dihedral group D2n, and then 3, the groups A4, S4, and then A5, where S is the symmetric group and A is the alternating group. And in these cases, the quotient S2 mod A5, this is the most exotic one, the quotient of the two-sphere by the icosahedral group is the 2, 3, 5 orbifold. In other words, in the quotient space, you have cone points of order 2, of order 3, and order 5. Here you have cone points of order 2, 3, and 4, and here you have cone points of orders 2, 3, and 3. And by the way, the dihedral group and these things, those correspond to the fact that those correspond to when I have 2 points here. And so I have to get a sum that's positive, like a half plus a half, or 1 over n plus 1 over n. Yeah, so the quotient here, I should say, this is the n orbifold, and that's the lemon again. And when you take the general lemon and you mod out by this symmetry, you introduce 2 orbifold points of order 2, and then you're left with just 1 of order n. So this turns out to be the 2 and n orbifold. 2 n orbifold. Okay, so even when we're looking at the sphere, there's a fair range of geometric objects to consider. And in particular, you might say, I want to see this group A5 more clearly. So how can I see geometrically what this quotient space looks like? Well, I can picture it in my mind. So the pictures of S2 mod A5. So the first thing you might do is you might say, I'm going to take the 2-sphere and I'm going to tessellate it by very special triangles. And if I could find these triangles such that there should be 1, 2, 3, 4, 5, if I can find the vertices of an octahedron, which I can't even draw, 1, 2, 3, 4, 5. Anyway, if I could tile the two-sphere in this octahedral pattern, then the symmetries of that tiling would be A5, and the quotient space would be my orbifold. And so my orbifold would look grosso modo like this. There's an orbifold point of order 2 here, 3 here, and 5 here. And actually, this quotient space has a sort of a front and a back. So I should color the front white and the black back. Then upstairs, what I would actually be seeing is a sort of, is a bicolored thing like this. This would be black. This would be the black parts would be the front and the white parts would be the back. And sorry, I miscolored that. Okay. So actually to create this tiling or to understand this space, it suffices to just construct one of these 2, 3, 5 triangles. And once I have a 2, 3, 5 spherical triangle, I can then reflect it through its sides over and over again until it tiles the sphere. Or if I'm really just interested in this space geometrically, I could take 2 copies of that triangle and glue them together back to back, and I would have the desired quotient space. So here's a question: how to explicitly construct a 2, 3, 5 triangle. Okay, so let me just as an exercise show you that this can actually be done. So one way to do it is don't construct the vertices, construct the sides. As we've seen, that's the golden root to the triangle. And this pair of sides is very easy because they meet at a 90-degree angle. So we might construct, say, this circle here and this circle here. Let me call those CA and CB. And then the real problem will be to construct CC. So we could, for example, take CA to be 1, 0, 0 perp. In other words, we take A to be 1, 0, 0. And then we could take CB to be 0, 1, 0 perp. And what's good about this is that A dot B is equal to 0. So that ensures that these 2 circles meet in 90-degree angle, CA and CB. And now along comes CC. So we don't quite know what CC is, but it's going to be given by some coordinates x, y, and z. And it's going to have the property that first it lies on the sphere. And secondly, that it has the right inner product with A and B. So we know that A dot C, if this is CA, that should be telling us about this angle here, which is pi over 3. So this quantity should be minus the cosine of pi over 3. And similarly, B dot C should be minus the cosine of pi over 5. And once we know those numbers, well, those are just x and y. And then z is determined up to sine by this equation. And so what we find is that c is just equal to minus cosine pi over 3 minus cosine pi over 5, and then some complicated square root, namely 1 minus this thing squared and that thing squared. Okay, so in fact, it's fairly routine to find a triangle on the sphere with explicit inner angles. It's especially easy when one of those angles is pi over 5. And once we've constructed that, we have an explicit construction of the action of A5 on S2, or at least generators for that action. Namely, we take reflections through these 3 circles. Those are 3 isometries of the sphere. Then we take the group they generate, and then we take the subgroup of index 2 that preserves orientation. That is the action of the icosahedral group, or the embedding of A5 into S3, into SO3. Okay, so this was sort of a preliminary warm-up to doing hyperbolic geometry. And what we want to do is try to mimic many of these constructions in the case of constant negative curvature, which is slightly less familiar. But we'll see something very similar. For example, there is a three-dimensional space, and the hyperbolic plane isometrically embeds in that three-dimensional space. It's just that space is not the standard Euclidean space. Okay, so now let's turn to models for the hyperbolic plane. And there will be 5. Okay, so remember, I like the idea of thinking of the Riemann sphere as a big space which is going to hold both spherical and hyperbolic geometry. So its symmetry group up to order 2 is SL2C, and then sitting inside of here we had SU2. This is the symmetry group of spherical geometry. Well, the symmetry group of hyperbolic geometry will also be a real form of SL2C. It's SL2R. So the first model is we take the hyperbolic plane, and in fact, this is such a common model that people use the same notation for the abstract hyperbolic plane and for the upper half plane, is just a set of complex numbers with imaginary part of z, which will often be denoted by y, being positive. Okay, so it's the upper half plane. The imaginary axis, here's I. And on this space, we introduce a metric, which is the Euclidean metric divided by y. So the Euclidean metric, of course, is not complete on this space, but by putting a y here, you make it blow up near the boundary. And since the integral of 1 over y diverges, the space becomes metrically complete. Now, the automorphism group of the hyperbolic plane as a Riemann surface is, as you all know, it's just SL2R modulo plus or minus the identity. That is, any conformal map sending the upper half plane to itself extends by Schwartz reflection to a map of the Riemann sphere to itself. So these automorphisms are all Mobius transformations. The fact that they preserve the real axis ensures they can be represented by matrices with real entries. And then, well, there are matrices with real entries that send the upper half plane to the lower half plane. We don't want those, and that's what the S does for us. If we didn't have the S, we could have something like 1, 0, 0, minus 1, which is just z goes to minus c. That doesn't preserve the upper half plane, but it's not in this group. Okay, and now the beautiful fact, and this is really one of the miracles of the theory of Riemann surfaces, is that any conformal automorphism is actually a metric automorphism. So these maps, which just preserve the complex structure on the upper half plane, are the same as those that preserve the hyperbolic metric that I've written down. And in fact, that's not too hard to see. For example, if you take a map of the form z goes to az plus b, translation obviously preserves this metric because it preserves the height y. If you multiply by a, you multiply z by a, but you also multiply y by a. So scaling the z doesn't change this metric. So in this metric, you should imagine that this happy person, this happy person, this happy person, they're all the same size. They're waiting in line to get their coded test, which is infinitely far away. Since the metric scales like 1 over the distance to the boundary, although these in the Euclidean metric are shrinking, in fact, they're related by, say, multiplication by a half, which is an isometry for the hyperbolic plane. Then one should check that z goes to minus 1 over z is also an isometry. This is an easy calculus calculation. I won't do the change of variables for you, but finally, these two types of transformations generate SL2R, prove this equality here. Okay, so before we talk more about hyperbolic geometry, let me just mention an amazing corollary of this accidental identification, the corollary is that almost all Riemann surfaces carry canonical metrics of constant curvature -1, inherited from the metric rho on H, which is usually isomorphic to the universal cover of X. Okay, so this coincidence between complex and hyperbolic geometry is a really powerful and unusual feature. Okay, so this is our first model. And as before, we might want to know, for example, what do the geodesics look like? So an example of a geodesic is, again, something like a longitude. So in fact, the imaginary axis, I times R plus, is a geodesic. And again, there are two ways to see this as a geodesic. One is that there's a reflection of the hyperbolic plane that fixes this line. So the unique geodesic from P to Q has to lie on the axis of symmetry. And another way is to observe that if you were to take a path from P to Q that's not along the imaginary axis, and then just project it horizontally to the imaginary axis, that wouldn't change the values of y. And so that map would shrink the length of the curve. And therefore, this is, in fact, the shortest arc between P and Q. So you can think of this as, again, something like a longitude going through the North and South Pole, except the North Pole is now the point at infinity, and the South Pole is the point 0. You can think of those as analogs of the North and South Pole on the Riemann sphere. Okay, and now, of course, Mobius transformations send circles to circles and preserve angles. So if we apply an element of SL2R to this geodesic, we'll get another geodesic. And the result will be a circle, because a line is a generalized circle, and it will be orthogonal to the boundary. Moreover, if you have any circle orthogonal to the boundary, you can always apply a Mobius transformation to move it so that its endpoints are at 0 and infinity. In fact, SL2R acts transitively on triples of distinct points on the real axis. So in fact, the geodesics coincide with the circular arcs, which are perpendicular to the boundary of the upper half plane. So the geodesics as geometric objects are equal to what we call them semicircles perpendicular to R hat, which is R union infinity, which is the boundary of hyperbolic space inside of the Riemann sphere. Okay, so another natural geodesic is, for example, the one through the point I up here. Okay, so if we believe these are geodesics, then we should be able to parameterize them by arc length. And that should be no more difficult than parameterizing the equator by arc length, which could be done by trigonometric functions. And as you can imagine, when we do this for hyperbolic geometry, it's the hyperbolic trigonometric functions that will enter. So let me just remind you that these functions are given by cos c is e to the z plus e to the minus c over 2, and sinh c is equal to e to the z minus e to the minus c over 2. They have the property that cos squared minus sinh squared is equal to 1. And then, as usual, something like tangent is defined by the sign of sinh over cos. secant is defined by 1 over cosh, and they satisfy similar laws. For example, tanh z squared plus secant z squared is equal to 1. Okay, so so now let me just mention how to parameterize IR plus as a geodesic. Well, this is easy. We just parameterize it by gamma s is I times e to the s. And in fact, if we take any 2 points on the imaginary axis, say IY1 and IY2, then the hyperbolic distance from y1 to y2 is nothing more than the integral from y1 to y2 of dy over y. And that's just the logarithm of y2 over y1. And so, for example, the distance from gamma 0 to gamma s is the logarithm of e to the s, which is s. And so by that calculation, this is the logarithm of e to the s, which is s. Okay, so the exponential function gives a unit speed parameterization of the imaginary axis. And that's consistent with this picture that we're drawing here. If I were to mark the points I over 2, 2i, 4i, etc., these points are evenly spaced in the hyperbolic metric. This distance is the same as that distance. So distances grow exponentially fast relative to the Euclidean metric, and consequently the geodesic's parameterization has to accelerate at the same rate. Okay, now what about this guy? The circle, the absolute value is equals 1 in the upper half plane. How do we parameterize that with unit speed? Well, this is a beautiful fact. So the absolute value is equals 1 as a geodesic. In fact, this is so nice, I think I'll draw a picture of it over here. It is parameterized by hyperbolic tangent and hyperbolic secant. So let's start at I, follow the circular arc down to 1. And a typical point here is given by, in x and y coordinates, by what? Well, it's the tanh of s and this hyperbolic secant of s. And indeed, the let me just remind you what the graphs of these things all look like. So sinh and cosh look like this. Cosh is symmetric and grows exponentially fast. It's asymptotic to e to the z over 2, or e to the x over 2. Sinh is odd, but it also grows exponentially fast. It gets close to cosh very rapidly. This is sinh. And so sinh over cosh, sinh is always less than cosh, so tanh starts at 0, and then it gradually goes up to 1. Kind of looks like the opposite of tangent in Euclidean geometry. And then secant starts at 1, and then it goes, hyperbolic secant starts at 1, and then it goes very rapidly to 0. Okay, so that's the parameterization of this arc, and gamma s is equal to this. And I think in the interest of time, I won't compute the speed of this parameterization. It is indeed 1. But what I want to observe is the following, that there is if I draw a line through this point here, what I get is a parallel to the imaginary axis, because these distances are all constant. These distances are all the same because scaling, multiplication of z by a real number, is an isometry. So this is not a geodesic, but it's a parallel to the existing geodesic. And there is a natural map that starts at this geodesic and goes out to this geodesic. And that map is an isometry for the Euclidean metric. But what does it do for the hyperbolic metric? What happens with the hyperbolic metric is the value of y gets smaller. And so lengths increase because the closer you get to the real axis, the longer things are. If I was a more distant parallel, you'd see the value of y has decreased radically. So if I move distance s, what's happened to the value of y? Well, it's gone from 1 here to secant s here. And secant is 1 over cosh. So let me just sum this up in a proposition. The parallel at distance s from a geodesic is expanded by a factor of cosh s. In other words, let's think intrinsically. When you have a geodesic, it's going along as fast as it can. Then you have this tube around it consisting of this parallel. Maybe you go up here distance s. This is all supposed to be at the same distance, so it doesn't look like it, sorry. Maybe I'll just draw it horizontally. You have this parallel at distance s. So you might say, look, let's just take a side route. Here we're going distance d. Why don't we just go a short distance s over here and then follow parallel to where we were and then go back? Well, this length here is cosh s times d, which is approximately e to the s over 2 times d. So if you decide to go 1 mile off of the road and stay a mile away from the road, then you're like driving 10 times longer than you needed to. So it's very inefficient to move away from the geodesic in hyperbolic space. And we'll use this calculation repeatedly in our analysis of hyperbolic geometry. Okay, so please read the course notes on the 5 models for hyperbolic geometry, and I will go over all of those next time.
Wait, one question about